Okay, we continue with the shear and moment diagrams for beam. So we talked before in the previous video, if the variations of V and M are plotted, functions here is plotted on the graph. So they are termed as the shear diagram and moment diagram or bending moment diagram. So basically, is the analysis of element at each point of the beam. So at each element we analyze the shear and moment value of the beam. So when you apply in the equation of equilibrium, we have summation of Fy is equal to 0. So in this diagram, you can see that shear force, the shear plus the distributed load times the distance x minus the shear plus the increment of shear is equal to 0. So the increment of shear is, you can cancel out this value. So the increment of shear is distributed load times the distance, the distance x, x small incremental distance of x. So we have anti-clockwise moments taken as positive. Summation of moment at 0 at naught is equal to 0. So your moment there is negative v times the distance x minus the moment in the section, then minus the distributed load, the moment from the distributed load, and then the load here, the load on the other side. So this is analyzing like a portion, small portion in the beam, small portion here. So this is a function. So you can see your increment of a moment is in power of 2, x power of 2 and x. So it is a quadratic equation. So by dividing x, delta x, and taking the limit as delta x nearing to 0, the previous equations become dv over dx is equal to wx, and then dm over dx is equal to v, as we discussed before. And when you differentiate the function of shear, you will get distributed load. When you differentiate the function of moment, you will get your shear value. So integrating from one point to another between concentrated forces or couples, in which case this value. So in order to account for concentrated force and moment, consider the free body diagrams of differential elements of the beam. So let's say this is your elements of the beam. So it is seen that force equilibrium requires the change in shear to be delta V is equal to negative F. So when you solve for this, so you get your delta V increment of in shear is equal to negative F. So for point load concentrated force of this F, so the value is a point, it's not a function. For example, the value will be just 1 point. Let's say it's the value of F is 10, so your graph would be here negative 10. So instead, if it is a distributed load, so there will be a quadratic function, like a curve graph, because your function is here a linear graph, because your function is x times x, where for moment is power of 2x. Basically, just want to show you how to differentiate when you are drawing a free body diagram, when you're drawing shear force diagram or bending moment diagram. The having knowledge of function due to that loading will help you determine how do you draw the graph. Because basically you are trying to find the value of shear, but you don't know what is the shape of the graph. Because if you didn't find the if you don't find this uh, shear and moment function, you directly calculate at certain point. So if you are doing that, you are calculating the value at certain points. So you need to know what kind of graph will be come out. So if it is a point load, it's like a square graph. It is like going down. It is a straight graph like this. If it is a distributed load, so you get your uh, linear graph. If it is has a power of 2, so you get your curve graph, because the value, the load, the nature of loading, because when it's point load, so the load is going down at a certain point, at one point where the load is acting. If it is a distributed load, so the load is applied gradually, increasing gradually up to a maximum point. If it is uniformly distributed, if it is a triangular load, so the rate of increasing is different. Huh? The rate of increasing affect your graph of the load, graph of the shear force diagram. Let's see the example here. So this is your shear and moment diagram for the beam. You have a pin roller and triangular distributed load of 20 kilonewton per meter at the peak here. So you have a 9 meter long beam, 9 meter long beam. At endpoints, x is equal to 0, v is equal to 30, and then at distance 9 at end of the beam, 9 meter, your shear will be negative 90. So the load W is negative and linearly increasing. Dx dv dx is equal to W. Linearly, as you can see, because it is a triangular distributed load. The point of zero shear can be found by using method of sections from a beam segment of length x. So at V, shear is equal to 0. So summation of Fy is also equal to 0. So your function of x is 30, your action here. And then this is your triangular distributed load. Triangular distributed load here. We just want to know where is the point that the shear is 0. Shear is 0. So it's equal to 0. So you solve for x, you get your x is equal to 5.2 meter, which is around here, more than half. Uh, it is important for you to be very careful on in this function of triangle. As we said before, the triangle is proportion. Triangular distributed load is proportionate because 20, you get a peak load 20 at distance of 9 meters. So you want to know at distance of x meter, what is the peak load. So it is a proportion. So 20 over 9 times x, distance x. And then you also need to time x because of the triangular loading. So that you get your peak load here. Peak load at distance x. Peak load at distance x. Peak load at here. You don't know peak load here. You need to do the proportion, triangle proportionate. Okay. From the shear diagram, 0 to 5.2, the value of shear is positive but decreasing. So dm over dx is equal to v. It's also positive. So your shear, basically your v is positive. So your graph, basically you are drafting. So you go up 30 and then it's decreasing due to that triangular load, then up to 5.2 here, 5.2 meter will be 0. This one is 0 shear. This is shear. This is 30 kilonewton. You can draw kilonewton here. V in kilonewton. So this is your distance in m. So basically, this is how you draft for the first half up to point 5.2. So you get 0 here, and then likewise from 5.2 to 9, the shear and So the slope of moment diagram are negative uh, and decreasing. But basically, it's a one graph, one graph as shown here. So the the moment is increasing, yes, but the shear is still the same, and that up at 60, which is, as you can see, 60 is similar to your reactions, because at end point at reactions will be sum up to zero back again. So it will be zero back again. So that's why there is a straight line upwards here, because that 60. So this is your final graph. So basically you can imagine the forces acting. So that's how the beam is trying to counter that force. So you have a force acting downwards in triangle, increasing, and then at directions spike up to achieve equilibrium. Okay, next is a bending moment diagram. So bending moment, as we discussed before, so we assume it's positive. So calculating your bending moment here, achieve equilibrium. So you analyze your moment here at point X. So we're analyzing at X equal to 5.2. X is equal to 5.2 meter. So there you have it, 30 times your distance X, value of X, which is 5.2. So your 30 is negative because clockwise. This is your triangular distributed load here. This is your peak load. This is a peak load of your triangular load. Draw triangular load here. And then this is your moment arm for that triangular load, which is one third of X. One third of X plus moment we assume positive. So you get your moment X, point X, which is the maximum is 104 kilonewton meter. So just a reminder, uh, we've discussed before the negative and positive, negative and positive here in the previous video. So previous video, as you can see here, whenever you are analyzing your shear force diagram for a beam or a frame, ensure that you assume this orientation, and then it is positive. So uh, the shear will be downward positive, and then counterclockwise positive. So that's how you come up with this positive value of shear here in this graph. So that's how you come up with, you section the beam, right? For example here, section the beam, and then you apply your shear force. You need to uh, assume that is downward, be positive. So if you draw this moment diagram, say you have 30 here, 30 kilonewton, and then you have distributed load of proportion to 20 over 9 times X, right? Here, peak load with the, and then if you sum out the equation here, V here, right? So it will be similar to this summation of y equal to 0, and you can have your 30 positive minus this triangular load, this 1 over 2, 20 over 9 x times x, right? And then your v your V is negative V equal to 0. So your V is equal to all of this. But since we assume that V is negative downward, so your graph will be positive value. If you have a negative value, if you say you get negative value, let's say this is the value of triangle is larger than 30, right? You get here like 60. So you get a negative value over here. So your V is equal to negative. So negative will be that negative would show that the graph is negative. Let's say here we have positive and then upwards 0, and then let's say it's negative because your V is actually upwards already. The alignment is important, and also to understand the point where the forces become negative or positive. I think the rule of thumb here is to uh, compare the reactions and the applied load. For example, here when you are drawing your shear force diagram, you see here it's 30 kilonewton upwards, and then your triangular rating downward is almost zero here at point at starting point. So you can expect the value to go spike up 30 kilonewton, then it goes down as the load increasing up until that point, your roller, and then it will be spiked up to zero back again. So you can expect there is a inflection point here, the point at which the shear force becomes zero. And then when shear force becomes zero, you have a maximum bending moment there. So you can expect your graph to have a peak there and then zero back again at the point, because you don't have any bending moment at end. So that's when we talk about bending moment. When you have a pin here and roller here, there will be no bending moment at end. So you expect a zero bending moment at end of the beam, unless it is a cantilever beam where you have a fixed support here. So you can expect a spike of bending moment, then can reduce until zero at the end. So this is more important because this is a combination of beams. Basically, you can say frame is a combination of two beams. So example 413, draw the moment diagram for the tapered frame shown. Assume support at A is roller and B is pin. So this is roller, as you can see here. This is a pin. So what you want to do is basically first is find your reaction. So this is your reaction from the overall body. You have applied 25 kilonewton here and 15 kilonewton horizontal. Then based on this, you get your 15. Okay? You can do some quick calculation. So this is 30 and 5 uh, based on the moment. If you resolve moment point here, then you can analyze the moment to find the reaction here, which would be 5 kilonewton. And then what you want to do is separate them into a section. Before the fixed point here, you can say that at the angle here is a fix. It's a fix when you cut here. So it's a fix. Sometimes you get the combination of pin. You have pin. So maybe when pin, so you can resolve pin. You don't have any bending moment, lah, right? For that, like this example. So when you solve, you cut into section, you can solve the reactions. So basically, this is your normal forces, which will be counted here, and then you have a horizontal forces acting here, then will be translated, will be counted by here in the section here 15 kilonewton, and then you take moment up at this point, so you get your moment, internal moment here, because you have a 15 kilonewton times the moment arm of 1.5. So you get your value of moment here, and then translate this into at the joint here. So just in the opposite direction. This one is clockwise, and then this one you can counterclockwise to the left, to the right, downward, become upward. Just translate. Once you translate that, you can find the forces here. You can find the internal forces here, 5 kilonewton, and then 15 kilonewton of normal force, which is due to shear of 15 kilonewton, and then the moment of 22.5, which is due to this 22.5 kilonewton. And this one is the product of this 30 minus 25, you get 5 kilonewton. So because you want to find this, because it will be translated into the next section here. So once you calculated all these internal forces, you can draw the shear force diagram. So this is the shear force diagrams for frame CB, member CB, and AC. I think it'd be best if you look at this. As you can see here, so there's a pin here, a roller here. So for member AC, here, for member AC, this one. So for your member AC here, as you can see here, member AC. So because of this load here, 1.5 kilonewton. So you get your triangle load, triangle load triangle load from the you get your triangular bending moment. Actually, this is a bending moment. So there's a question stated that you need to find the bending moment. So basically the shear force diagram will be square at this, and for this one, so square, because when you draw your shear force diagram, it will be negative 15, then go upward back to 15, and then you achieve equilibrium. For this one, uh, so this one start from here, so you get your 5 kilonewton, and then going downward until 5 kilonewton. We have 5 kilonewton, and then up until here, and then goes down. So basically, when you have a like a not linear but a flat constant graph like this, so for your shear force, like bending moment diagram will be a triangle, a linear graph lah. So that's why you come up with this value. So if it is calculated as a function here, a function of bending moment diagram will be this one here. Maybe is 15 times x, 15 times x. As you go, as you analyze from 15 point here up until the end member, so you get the value will be increasing lah, up to 1.5 meter. So that's why your value is linear. This is linear relationship, linear graph. Same goes to here. The function will be 5 times x, 5 times x. But you have a moment here. Same goes to here. You have a moment here, 22.5. So at the end of the analysis, at the end point, you need to add 22.5 kilonewton meter. So basically, when you draw your shear force diagram, any moment of shear force diagram would be easier to show like this. So this member, so at point 15 kilonewton, you get increasing bending moment and then a sharp increase due to 22.5. And then at here, you have a sudden drop, like sharp, steep, like vertical drop of 22.5 due to this value, this moment here, internal bending moment, and then it'll be reduced due to this forces of 5 kilonewton times the length from 0 until 4.5. So the moment is increasing with the increasing in moment arm up until 0 because you have no bending moment there. Okay, some last part, a technique. This last part is a technique. If you are facing problems or with combination of load. So this is called method of superposition. Beams are used primarily to resist bending stress. It is important that the moment diagram accompany the solution for their design. It is important for you to draw a bending moment diagram. So most loadings on beams in structure analysis will be a combination of loading as shown. So it's combination. Either it's a point load. Let's say we have a cantilever beam. You have a point load at the end, and then you have a moment at the end. So if you draw your bending moment diagram, there will be a triangular bending moment diagram due to this point load, where you have a moment here. That's why you have a spike here, like a vertical value here of P times L, which is the reaction here, moment reaction. And then the reactions reduced, counted by the reducing forces up to the end. There's no moment. That is for point load. If you have a point moment here acting at the end, so you get a, you get your constant moment, um, constant moment uh, uh, internal, that acting internally within this beam. So that's why you have constant. So method of superposition is that you can combine these two. You combine these two to become a single bending moment diagram. So you add these two bending moment diagrams, you get the resultant bending moment diagram. On another example, if you have your UDL, uniformly distributed load, so say here, so your curve will be parabolic curve. If it is a triangular load, it will be a cubic curve. In principle, it is a reducing moment that we are seeing here. The moment is reduced up until the end, as there's no load and no moment there. But the function is a bit different. It's a cubic curve because you have a different denominator because of the type of loading applied, type of distributed loading applied. Um, and then the method of superposition is basically like this. If you have a beam like this, and pin roller B, then you have a distributed load of 40 kilonewton meter, half of it, and then you have a moment at the center of it. You can basically uh, uh, disassemble. You can solve it separately, as shown here. So you can solve it by applying here the forces here separately. So you have 40 kilonewton in this cantilevered beam, plus the moment acting at the center, cantilever beam, and then a cantilever beam of point load because of the reaction here. So this method is a superposition method where you separate the loading to solve for a more simpler solution, and because of the combination load. As you can see here, uh, we are changing the support into fixed because of this one, because we are using the method of superposition of cantilevered beam, so we can expect the graph to be like this. So the most important thing is that you are removing the load, each of the load according to the type. For example, say UDL, you just neglecting the moment here, and then reaction at B, and then you change the support at A to become fixed support. So and then you get a graph of this one will be similar to this, which is a parabolic curve. So you get this parabolic curve here, and then for this moment you get a curve here, and a flat graph here, which is down here. And the last one, a point load, you get, because it's upward, so you get inverted triangle here, you get here. So adding all this, you get, I think, somehow like this, somehow something like that. So method of superposition helps you uh, in solving the many moment diagram separately, which is easier because you don't have to analyze each point. You can do the traditional way, but method of superposition is a lot more simpler because you can analyze this function here separately, and then this function here separately, and then this one. If you have three functions, you have three functions. This is a flat function, will be easier, which is negative 750. The function is negative 750. It's negative 750, and this one is function here negative 40 times x squared, L squared, x squared, whichever you suitable for you, divided by 2. So this one plus this one, but this one is up until 5 meter only, 5 meter only. L is equal to 0 to 5 lah, 0 to 5 meter only. Beyond the 5 meter, it will be stagnant. The maximum will be like 500 kilonewton. And then the last one is this formula. This formula is negative PL, negative PL, which is inverted. So it is inverted, which is PL. This P is 1 to 5 times L. L ni 0 to 1 to 10. So basically you plus these two, you get your shape of your graph. Say at x equal to 1, for example, x equal to L equal to 1, and L equal to 1. So this will be 20, at L equal to 1. This will be 20, negative 20. This will be same 750. This one will be 1 to 5 positive. So minus is I think get like 595 word negative. So x equal to 1 negative. Then you can plot your graph. Simpler. You don't need to analyze. You don't need to. You don't need to find a function because if you don't do this, then it will become more complex. Huh? For example, the function at end of beam at end of distributed load. For example, at 5 meter, 5 meter. So you need to analyze this first. Then you need to know the shear value and the moment value here, and then at the midpoint there, after the moment, then you need to know the value, and after the moment point here, example at point 6 x equal to 6, need to find the value. So it is simpler compared to other, because you already have your function, standard function for shear. Just a reminder that since you are changing your support from simply supported to a fixed and cantilever, uh, um, just remember that in order for you to distinguish all the forces, um, be mindful that you have two forces here and then the roller here. Be mindful that you need to include the reaction at another endpoint that will become free from support here, free from support here, to add one more free body diagram for that reaction, because there is the applied load also, because it is actually a point load at first. So it's simply supported. So when you are having the simply supported beam, the method is to change it into a cantilever beam, but add also a free body diagram for the reaction of the roller. Be mindful of that, because you might get a different diagram if you forgot to add this free body diagram. That will be all for your beam lecture. Maybe we add some video for exercise and books. You can find this online. The reference being posted online on anyflip.com. You can see here anyflip.com. Let's see here, it's anyflip.com. You find anyflip.com, you can find the books reference, so you can do your self-studying, self-learning. A lot of more complex frames for you to study. Maybe we can add more videos on discussion on this, so we can study together. So see you next video. Thank you very much. Thank you for your attention.